So rational functions. I just realized there's a little lag there. All right, so the section has the domain of rational functions, arrow notation that is specifically for calculus. Vertical asymptotes just means that there is a place where the graph does not cross. Horizontal asymptotes are not that important. It kind of becomes important in calculus, but it's not that detrimental here. Transformations of functions, it's the same thing as when you have the vertex form and you transform, or you take a quadratic and you transform it. It's the same thing with rational functions. Slant asymptotes, not even really important at all. And rational functions and applied problems are mostly going to be something that's related to like when you get kind of like to physics. So a rational function you see here is defined, how it's defined, P of X over Q of X. That just means like a numerator and a denominator kind of thing. And then the thing with rational functions is you cannot divide by zero. So anything that makes the denominator zero is not allowed. They use kind of a huge rational here, but normally when you learn them, you start off pretty simple. So finding the domain, right? So really what you're looking for when you're doing rational functions is anything that makes the denominator zero, which for A, it would be 3, right? So then when you come down at the bottom, it says the domain of F is X. All X is such that X does not equal 3. So that's how you read that. And then the domain of F in interval notation. So the first one's set builder notation, and then the second one is interval notation. So negative infinity up to 3 is a union of 3 to infinity. And if you graph it on Desmos, you can see what that looks like. So it says, I like the little great question thing where it says, other than observing the denominator, is there a procedure I can use to find the domain of a rational function? So it says yes, because the domain of a rational function is the set of all real numbers except for those for which the denominator is 0. You can identify such numbers by setting the denominator equal to 0 and solving for X. It's that simple. For part B, we have 2 numbers that cannot, X cannot be, and that is going to be -3 and 3. You can factor them, or you can just set X squared minus 9 equal to 0. And when you solve that for X, you're going to get plus or minus 3. Okay. The third one, it says that there are no real numbers that would make the denominator 0. And that's because you cannot do the square root of a negative number. So when you set X squared plus 9 equal to 0, you're going to get X equals plus or minus 3i. And that's not a real number. As I think I shared with you before, there are videos that you can look at to be really, really specific. This can be very cumbersome, but what you're really looking for when you're doing functions like these, where you have X squared in the numerator and so forth, you're doing the same thing. You're plugging in numbers for X, and then you're seeing what's really happening. This is a definite calculus topic. The notation down here, it says, it's called arrow notation. So the way you read it is as X approaches 0 from the left. So the little minus sign means from the left. F of X approaches negative infinity. And that's the way the graph falls. When you first take calculus, anybody in here that's going to take it, limits, it's called limits. It's the first thing that you do when you get to calculus. It's a pain. I didn't like limits at all. It kind of ties itself together and it becomes interesting over time. But you will see this notation, this arrow notation, a lot in limits. And there's all kinds of ways to see this. So you can see it on the graph. You can see it on the chart. You can trace it with your finger. You can use a graphing utility. You may need to adjust your window on let's say a TI 84, you know, but it's just, you know, it's just you're really just interpreting what you see on the graph. So you can spend time on that if you're really interested, and if you are going to take calculus, you might want to make sure that you read this with a fine-tooth comb. So it says what happens to the function as x gets further away from the origin. So you plug those numbers in, and then you see that they plug numbers in that are big, you know, 1, 10, 100, 1000. That's also called a logarithmic, I believe it's logarithmic scale. And 1 over x is one of the functions they use a lot in calculus too. So you just, you know, if you look at the figure, it's just showing you which way the behavior of the graph. And you do that a lot. You do that a lot where you're analyzing what you see. I try to tell my high school students that I don't know, it kind of just goes over their head. They're like, what do you mean? I was like, well, what do you see? And they'll either just use words like up or down. And I'm like, well, can you look at the X and Y axis? You know, start to discuss, where do you see the graph going? You know, the arrow is the direction. You know, be a little bit more specific. So there's still the reciprocal function. This is just a little chart, you know, how to read it. So you see the symbol X approaches A from the right, X approaches A from the left, X approaches infinity, X increases without bound, and what X approaches negative infinity, and it decreases without bound. Stuff like that. This is 1 over x squared, which is another one that they use a lot in calculus. So this is it says Blitzer bonus, and it says, would it surprise you to find out that a region that extends indefinitely can have finite area? Area is something called integration when you are studying calculus. They're called integrals. And you will be, those of you that I know will be taking it, it's probably going to be drilled into your head. You're going to be nauseous from it. I can't tell you how many times I heard the professor say the area under the curve. I'm like, can't you please stop saying that? What is the area under the curve? Yeah, it kind of drove me crazy. But anyway, so if you look at the graph of 1 over x squared, the shaded region in the figure bounded by x equals 1 on the left, f of x equals 1 over x squared, and the x-axis is unbounded on the right. It extends indefinitely to the right, but in calculus, that area of the region is 1 square unit, which is a finite area. Don't ask me to even try to remember how to calculate that. I don't even remember. But vertical asymptotes. So it kind of leads you into the asymptotes and what it really looks like, right? So think about it like this. Asymptotes just means where the graph is never going to cross. Is there anyone that does not understand that? Because it is kind of tough to grasp it in your mind. So let me know if you, let me look at the chat. Okay, nobody said anything. All right. So the notation is it's a bit much. It's very technical, right? And as anything, you need practice to get used to it. Even to this day, when I look at limits, I'm like, I have to sit there and think, okay, which way and what am I looking at? Limits can be a lot. But all it's really saying is if I'm looking, let's see if I can trace. Oh yeah. Okay, so it says here as X approaches A, and you see the line A, and I'm looking at the first graph in the bottom corner. So if you take your finger and you go across, right? Which way is, where is the graph going? It's headed up to infinity. Now it's gonna not constant, it's gonna consistently move up, but it's never gonna cross that line. That dotted line that says A, it's never gonna touch it, it's never gonna cross it. It's gonna get really close. It'll get really, really close, but it's never gonna cross it. Okay, so hopefully, let me know if you have a question about that or like how you think about it. And then the same thing with the other three, since it's kind of like a review for the test too. Yep, you're welcome. So again, and I can't stress this enough, I say it as much as I can, but if you are going to take calculus, you are going to do what's at this place right here in this little blue box. You're going to do it constantly in Calc 1. It is how Calc 1 begins. It was painful for me, I'm just gonna tell you. Here are some other examples of rational functions. They get a little bit interesting. You have sometimes where you have the shifting, but this particular one, part A, right, is this graph of part A. It says we want to find the vertical asymptotes. Now, sometimes when you have an X in the numerator, it changes stuff a little bit. But in this one, you just factor, and then it says there are no common factors in the numerator and in the denominator. The zeros of the denominator are -3 and 3. And it just has the vertical asymptotes. The only thing with rational functions is I really think that it's helpful to have a graphing utility because you kind of really don't know what's happening, because there's 3 different parts to the graph. So I think it's important to, especially I think with this test, you might need to match some things. Okay, and then for part B, when you factor the denominator, you do have a common factor. So what happens is, I'm trying to see if they have it on here. Okay, so it says the only zero, because you factor out X plus 3 in part B, it says the only zero in the denominator is the line X equals 3. It has a vertical asymptote. They don't say anything about holes. Okay. So I'm not gonna say anything about holes yet. And then in the last one, it is no real number. Oh, it's X squared plus 9. So there is no real numbers. So the curve is smooth. All right. Then we have some technology. So I don't know. I'm gonna try it. I have the Inspire on this iPad. Let me see what happens. Okay, so we're gonna try the graph. So X divided by X squared. Oh man, put a capital X. We don't want capital. X squared minus 9. And there's the Inspire. So I don't think I've used the Inspire in this class yet. I actually haven't been playing with my Inspire for a while because of state testing and all the other nonsense, and I haven't used them. But there is a way, let me see. There is a way to graph the asymptotes. I'm trying to see if I remember. If I do backwards, nope. That's not it. That's not it. That's y equals. Oh, I don't remember. I don't remember. There's a way to graph the asymptotes on here. Fire. So f of x equals x divided by x squared minus 9. And then I can graph x equals -3 and x equals 3. And then that way you can see, and I think you can change, yeah, you can change it to dashed lines so it looks just like the book. So if you want to be fancy, if you even want to be even more fancy, I think you can make these the same color. I think I've gotten better at this over time, especially on the iPad. So if you want to check to make sure that you put these in the proper spot, you can also label them. Right? So like, say for instance, you do this and you're on the test and, oh my God. And, can you give me the dot? No, I'm in the wrong one. That's the problem. I'm in the wrong one. I was like, why isn't it giving me the label? So like, say for instance, you did something wrong, but you were able to verify it with the calculator, with the Desmos calculator. Well, then this is what you would draw, showing your work. Okay. You can also show a table if you really want to be precise. So, I don't know what good points would be, but you see there where it says 3 is undefined. I don't know what will give you easy points to plot, but you notice they're all decimals. Decimals are hard to plot. I'm just going to delete them because that's terrible. So, you know, you can do your best, with some of the points. But rational functions are tricky. So it says, do I have to factor to identify a rational function's possible vertical asymptotes or holes? Yes. So for this example, you have x squared minus 4 over x minus 2. And when you factor x squared minus 4, you can factor out a x minus 2. And there you have a hole in the graph. Knowing where the holes are also is important when you take calculus. So, but when you get there, you'll know because your professor will tell you. And then there's some definitions of the horizontal asymptotes. I'm not sure if I put any on the exam for horizontal, but we'll see. So there are steps for locating horizontal asymptotes. They're not as important as vertical ones. And it just depends. So that rational function is just the a sub n x to the n plus a sub n minus 1 x to the n minus 1. That is just a form. It's just telling you, that you have descending powers. So say for instance, you go from x to the 5th, and the next one would be n minus 1, which would be x to the 4th, and so on, down to your constant term. So if the degree of the numerator is less than the degree of the denominator, the horizontal asymptote is y equals 0. And then if the numerator and the denominator, the highest degree is the same, it's the line of the coefficients. So A is the coefficient of the numerator, of the terms in the numerator, and B is the coefficient in the terms of the denominator. So you just divide those two. The example makes more sense. And then if the degree of the numerator is greater than the degree of the denominator, then the graph has no horizontal asymptote. So for the first one, clearly the degree of the numerator is less than the degree of the denominator. So the horizontal asymptote is y equals 0. Where is that one? Right here. So as you can see in this graph right here, let me make sure you see that one. These arrows, they're going to get really close to 0 to the right and really close to 0 on the left, but it's never going to cross. So that's what that looks like. I love the book for that reason. For this one, for part B, the exponents are exactly the same. So when you divide them out, you're going to get 4 divided by 2. And so the horizontal asymptote is y equals 2, and you can see it here, right here. Sorry, the other page is trying to creep in. So that's what that graph looks like. And then in part C, that's a strange looking graph. It's kind of like a sideways cubic function or something. I don't know. It's kind of like, looks like a line. It has a little squiggly in the middle. But the degree of the numerator is 3 and the degree of the denominator is 2. So there is no horizontal asymptote. Transformations, it's the same thing as before. You would just take the common parent function. So the parent function will be y over x, 1 over x. And then the other one is 1 over x squared. So those are what the parent functions look like. And then they tell you the odd and even if it's an odd and even function. And then if it's an odd function, the origin is, the symmetry is in the origin. And then if it's an even function, the symmetry is over the y-axis. Again, this is where graphing utilities come in handy. So you see here, you have the 1 over x squared. And then what are we doing to x? Well, we're shifting it to the right by 2. So you see where it says 1 over x minus 2 squared. So I'm shifting it to the right by 2. And then it says plus 1. So I'm just moving it up 1. And that's it. So it's the same thing as when you did quadratics. And then there's strategies for graphing. So I don't know how good this will do for you to write this down, but there are videos in here where you can go step by step. So I encourage you to do that. Yeah, I mean, you can go through this through your book and I would definitely write down the examples in here. All right, what time is it? Oh, it's almost 6. But yeah, so you can see there's a lot of steps to it. So I would do the examples, I would do the videos, and then I would, see if you can come up with your own strategy or strategies to what makes it simple for you. It is not easy to graph fractional points. It's the one thing that I always disliked about rational functions. So I would use, a combination of writing and Desmos to help you with plotting points. It's just not easy. All right. And then there's some more examples here. And steps to those examples. There's another example. Slant asymptotes. It's just, you just follow what they're doing. I don't think I have any slant asymptotes on the test. So I'm gonna skip over that. But feel free to go over that. they're not that important. I don't ever remember seeing a slant asymptote except for maybe in one spot in one teeny example. And then we have, what is this, a cost function? Yeah. So that's an application of what you would use it for, but it's a little unusual. It's kind of hard to make applications of this, except for in electrical engineering. What does it say here? Be sure to use the chapter test prep on YouTube for each chapter test. I didn't know it was on YouTube, but it says it is. And then, like I said, there's always the chapter 3 test, and you have the answers to that. So if you need to cram a bunch of problems in, these are usually challenging as well. So I recommend you doing the chapter test. All right, I am going to go back to well, actually, I'm going to use the review for chapter for 3.6, because I definitely don't have anything on the test from 3.6. You see how tiny it is. So polynomial inequalities, and how they're expressed. You're just taking a function, and then you can make it either less than or greater than, or less than or greater than, or greater than, or less than or equal to, or greater than or equal to. And that's something that is raised to a power greater than 1, possibly. And then rational inequalities, those are just the same thing, but with numerator and denominators, just like we just did. Since we're here, I'm just going to use this as a little short burst of variation. So variation it pretty much creeps up in a subject called linear algebra. That's the only time I've ever seen it. There is a little bit of a connection to variation when you are doing predictions. So there's a part of calculus where you need to predict what is going to happen to the function if you have something particularly in the, like if you put, okay, let's put it this way. So let's say you have a fraction. You have 1 divided by 2. Everybody knows that the decimal for 1 divided by 2 is 0.5. So how does it change if I change the 2 to a 4? Does it make the number smaller, or does it make it bigger? So just think about that. So the way that I think about variation, when it varies inversely, which is the more important one. The proportional one is, but the inversely proportional one, it'll suggest what happens to this function if I put a large number in the denominator. Will it go fast to close to infinity, or will it's almost like saying, does it rise or fall very quickly, or does it move slowly? Does it, and so it depends on what number you put in the numerator or the denominator. All right. So question 1 is going to ask you about the vertical asymptote. And I'm probably going to go through this a little quickly. Polynomial leading coefficient test, right? So it depends on the degree. Finding the X and Y intercepts. I'm sorry, X intercepts. There are, let's see, A through E parts. So you have, there's the Y intercept. You have to discuss the symmetry. And then you have to pick the right graph. I don't know why that's cut off, but you have to pick the correct graph. So it looks like a lot, but you know, that part A is multiple choice. Some of the parts are multiple choice, but then you have to fill in the blank. So you have to put in the right thing. So I want you to know that, like, for instance, if you put parentheses in here, it's going to mark you wrong. So make sure that you do what it says. Type an integer or decimal, use a comma to separate answers as needed. Type each answer only once. So be careful. Then you have a question. The perimeter of a rectangle is 68 feet. And you know that the perimeter is 2L plus 2W. If the length of the rectangle is represented by X, its width can be expressed as 34 minus X. And then the area is going to be the width, the length times the width. Finding vertical asymptotes, you need to factor the numerator. And then you probably are factoring out something. So there are no vertical asymptotes here, so be careful. This one, you need to factor the denominator. So you put the vertical asymptotes in those boxes and select the right one. The factor theorem, that's kind of a giveaway because you know it's X minus C, it's never X plus C. Remember, that's the form you put it in. And then in this one, you're just going to, it says to divide that polynomial by X minus 6, the first step is to write, and then you just fill in the blanks. Simple enough. And then here's one, like it was in 3.5. You are just describing what happens as X approaches -2 from the left. So if you take your finger and you go across the graph and you get to -2, which way is it going? It's going up to infinity. And then you have long division. You get to do that on paper and then you just fill in the blanks. But remember that you have to put, even if you have no remainder, you need to put the 0 in there. So be careful about that. I've seen that a million times be a mistake, a little small mistake. Again, another one with vertical asymptotes. And then you just determine if this one is correct. So all the work is there for you, just determine if it's correct or not. And then this one would be something that is, you have to be careful about how you put it in. So you have your, your restriction on the domain. So you have to make sure that you put the parentheses in the right spot, the comma, don't make any spaces, you do your minus, do your union. So just be careful. Transformations, self-explanatory. Now, again, I put these in the right order. So you see here where it says 3.5 and then this is 3.1. I just fixed that. So if it happens, I didn't mean for it to happen. If it ends up putting it in some kind of random order, I'm sorry. But I just fixed it. So for this one, simple enough. It says use vertex and y-intercepts, so you just graph it. Be very careful because the software wants you to graph that vertex and the y-intercept only. The axis of symmetry is the first, sorry, it's the x value of the vertex or the h value. They're the same thing. So x equals h. The domain, you have to know the domain, and then you have to know the range. So be careful with that, and be careful how you put the range in. Another problem with long division. Here's just some steps for long division, what they're called. It's kind of like definitions kind of thing. And then there's another long division problem. Same thing as before. I think someone asked me what does C7 mean. It just means this is a concept. So it's more of a conceptual problem. So it's chapter 3, section 3, but it's concept number 7. Again, finding the coordinates of the vertex, you know how to do that. And then this question is, what are we doing here? Are we just simplifying? I think so. We're simplifying, and then we're finding the result of that and then graphing it. And you have a restriction on x equals -6. And then this is vertex form. We have another long division. Doable so far? What do you think? You can give me a thumbs up. Let me see. Not too bad, right? Not too bad. I don't try to like make your head burst, especially since, probably gonna feel enough pressure as it is. And then there's another one. So you see that the exam is mostly heavily on long division. There's more problems with long division and synthetic division, kind of the setup of synthetic division. And then another, what is this? This is section 5. So this is just discussing which way you shift. That's probably the easiest problem on the whole exam. And then, discussing the asymptote. It says here, what is the asymptote? Does it have a vertical asymptote? And where it's located. And I think that's it. Yep, that's it.